The universe is vast, mysterious, and full of questions we still can't answer. From strange signals in deep space to phenomena that defy the laws of physics, some mysteries seem almost too bizarre to be real. In this video, we're diving into some of the most mind-bending, unexplained mysteries of the universe. So if you're curious about the unknown, make sure to hit that like button, subscribe, and buckle up because things are about to get weird. There's something hauntingly beautiful about looking up into the night sky. For thousands of years, humans have stared at the stars in wonder, mapping constellations, charting the movements of the planets, and pondering the nature of what lies beyond. With our eyes, then with telescopes, and now with satellites and space probes, we've slowly peeled back the layers of the universe, or so we thought. Because the truth is, everything we've seen, all the stars, all the planets, all the galaxies, all the light in the universe, makes up only a tiny fraction of what actually exists. According to our best scientific estimates, what we call normal matter, everything made of atoms, accounts for less than 5% of the total mass and energy of the universe. Another 70% is something we call dark energy, and we'll get to that. But the remaining 25%, that's something called dark matter. And we have no idea what it is. This is a story about absence, about something that should be there but isn't visible, a hidden presence that has shaped the cosmos since the beginning of time. It's one of the most profound, unsolved mysteries in all of science. And it all began with a problem, a simple problem of mass. The first clues came in the early 20th century when astronomers began studying clusters of galaxies, enormous systems where hundreds or even thousands of galaxies are gravitationally bound together. In 1933, Swiss-American astronomer Fritz Zwicky was observing one such cluster, the Coma cluster. It was vast and beautiful and strange. When Zwicky calculated the gravitational mass of the cluster, how much matter was needed to keep the galaxies from flying apart, he found a huge discrepancy. The galaxies were moving so fast that according to Newtonian mechanics, they should have escaped the cluster long ago. And yet they hadn't. They were still there, orbiting in what appeared to be a gravitational dance. But something was off. The visible mass, the stars, the dust, the gas, wasn't enough to explain the observed gravitational forces. There was something missing. Zwicky proposed a radical idea, that there was some kind of invisible matter holding the cluster together. He called it Dunkel Materie, dark matter. It was invisible, undetectable, and massive. It had to be, or else the math didn't work. But Zwicky's idea was ahead of its time. Most scientists dismissed it. After all, why believe in something you couldn't see? It would take another few decades before the idea of dark matter would resurface, this time from the spiral arms of galaxies themselves. In the 1970s, astronomer Vera Rubin and her collaborator Kent Ford were studying the rotation curves of spiral galaxies, essentially measuring how fast stars were orbiting around the galactic center at various distances. In a simple system governed by gravity, the expectation was straightforward. Stars closer to the center, where most of the mass is concentrated, should orbit faster. Stars further out should orbit more slowly. This is exactly how it works in our solar system. Mercury, closest to the sun, zips around it quickly. Neptune, much farther out, moves slowly. But Rubin saw something that defied this logic. The stars in the outer edges of galaxies weren't slowing down. In fact, they were moving just as fast, or sometimes even faster, than the stars near the center. This didn't make sense. If there wasn't enough mass in the outer regions to pull these stars inward, the galaxies should be coming apart. But they weren't. The only explanation was that there was a vast, invisible halo of matter surrounding every galaxy, something massive enough to generate the gravity needed to hold everything together. And once again, it couldn't be seen. It couldn't be detected through light. But it had to be there. Dark matter had returned. This time, the scientific community paid attention. Over the next few decades, evidence for dark matter continued to build. It showed up in the large-scale structure of the universe, the way galaxies cluster and form vast cosmic webs stretching across space. It showed up in simulations of the early universe, which only made sense if dark matter was included in the models. And perhaps most compellingly, it showed up through a phenomenon predicted by Einstein himself, gravitational lensing. Gravitational lensing occurs when light from a distant galaxy passes near a massive object, like another galaxy or a galaxy cluster, on its way to Earth. The massive object's gravity bends the light, distorting the image of the background galaxy. It's like looking at a distant object through the base of a wine glass. The image warps and twists. Astronomers began seeing these distortions in places where there wasn't enough visible mass to account for the lensing. Once again, dark matter seemed to be doing the bending. And here's where the mystery deepens. Despite the overwhelming gravitational evidence, we have never directly detected a single particle of dark matter. Not one. It does not emit, reflect, or absorb light. It doesn't interact with the electromagnetic force. It doesn't clump together like regular matter. In fact, the only way we know it's there is through its gravitational influence. This has led scientists to theorize what dark matter might be made of. One of the leading candidates is a class of particles called WIMPs, weakly interacting massive particles. These hypothetical particles would have mass, but interact so weakly with normal matter that they could pass through the Earth and through you without leaving a trace. If WIMPs exist, there are trillions passing through your body every second. Other candidates include axions, which are ultralight particles that could behave like a kind of cosmic field. There are even more exotic ideas, like sterile neutrinos, particles that don't interact through any of the known fundamental forces except gravity. But so far, all these are just ideas. We haven't detected any of them. To find these elusive particles, scientists have gone to extraordinary lengths. Deep underground, in old mines and specialized labs, detectors are shielded from cosmic radiation and background noise. These facilities, like the Gran Sasso Laboratory in Italy or the Sanford Tepa Underground Research Facility in South Dakota, are some of the quietest places on Earth. Inside them are vats of liquid xenon and crystal arrays designed to catch the tiniest flashes of light or heat that might occur if a dark matter particle interacts with a normal atom. There's also hope that particle accelerators like the Large Hadron Collider at CERN might produce dark matter in high-energy collisions. If a collision results in energy or mass missing from the expected outcome, it could be a sign that dark matter has been created and escaped detection. But so far, nothing. We have not seen a dark matter particle. We have not detected one. We have not created one. Every time we think we're getting close, the mystery slips away again, like a shadow at the edge of our vision. So now, some physicists are beginning to question the foundation itself. What if dark matter doesn't exist at all? What if the real problem is our understanding of gravity? This line of thinking has led to alternative theories like MOND, modified Newtonian dynamics, which suggests that gravity behaves differently at very large scales than we think. These ideas remain controversial, but they highlight just how deep the mystery runs. We may be facing not just an invisible form of matter, but a fundamental flaw in how we think the universe works. There's a kind of poetic irony in this. For all of our scientific advancement, all our telescopes and equations, all our simulations and discoveries, the universe is still mostly made of something we don't understand. We call it dark matter, but that's just a placeholder, a label for the unknown. The cosmos is whispering secrets, and we're trying to listen. Every galaxy we see, every gravitational distortion, every unexplained rotation curve is a clue, and yet the final answer remains just out of reach. We are explorers, yes, but we are also blind travelers, moving through a cosmos shaped by invisible forces, bound together by something we cannot see. Dark matter is not just a scientific mystery. It's a humbling reminder that for all we know, we've only just begun to scratch the surface. There's a kind of irony to it. The more we learn about the universe, the less we seem to understand. The deeper we stare into the void, the more it stares back, silent, indifferent, and full of questions we are not yet wise enough to answer. We ended our last journey with a realization that dark matter, whatever it is, makes up roughly 25% of the universe's energy matter composition, that it's invisible, doesn't interact with light, and doesn't clump together like ordinary matter. And yet it dominates the gravitational landscape of the cosmos. Now we're going to descend even deeper into the methods, the machines, and the minds trying to solve this riddle, into the long, quiet war waged in the coldest places on Earth. Because even though we've never seen dark matter, humanity has spent decades and billions trying to hunt it. Let's start underground. Far below the Italian Apennines, buried beneath nearly 1,400 meters of rock, sits the Laboratory Nazionale del Gran Sasso. It's not your average laboratory. It's shielded from cosmic rays and background radiation, making it one of the quietest, most pristine environments on the planet. Inside this sanctuary of silence, scientists have operated the Xenon 1T experiment, a gigantic detector filled with 3.5 tons of liquid xenon, chilled to a frigid 95 degrees Celsius. Xenon is perfect for dark matter detection. It's dense, inert, and its atoms are sensitive to faint interactions. The theory goes like this. If a WIMP, a weakly interacting massive particle, were to pass through Earth, it might occasionally strike a xenon nucleus. That collision would produce a tiny flash of light, followed by ionization. That flash, that whisper of contact, would be recorded. The detectors are so sensitive they can detect even the faint radiation from bananas. Yes, bananas. But despite the precision, the patience, and the promise, no definitive WIMP signal has ever been found. Not in Xenon 1T. Not in Lux. Not in Panda X. Nowhere. This silence is not failure, it's refinement. With every year, the detectors get larger, colder, quieter. The absence of a result doesn't mean we've found nothing, it means we've ruled out what dark matter isn't. And that's progress in disguise. Still, the implications are staggering. We've spent decades assuming that dark matter is a particle, that it's just hiding from us because it barely interacts with normal matter. But what if we're wrong? What if it doesn't interact at all, or interacts in ways we don't yet know how to detect? The nature of dark matter may not be as simple as we once hoped. Let's shift for a moment from Earth to the stars. In recent years, astronomers have been pushing telescopes to their limits. One of the most incredible instruments we've built is the European Space Agency's Gaia Observatory. Launched in 2013, Gaia's mission is to chart a three-dimensional map of our galaxy with unprecedented precision. It measures the positions, velocities, and brightness of over 1 billion stars. Why does that matter? Because dark matter, though invisible, leaves fingerprints in the motion of stars. The way stars orbit in galaxies, how fast they move, whether their paths wobble or twist, reveals hidden gravitational influences. By carefully analyzing these motions, Gaia provides new, high-resolution maps of where dark matter is likely to be clustered within the Milky Way. And what it's revealing is surprising. There appear to be vast, complex structures of dark matter, streams, filaments, clumps, interwoven through our galaxy like a ghostly skeleton. Some models suggest that smaller galaxies orbiting the Milky Way may have once been torn apart by dark matter's gravity, leaving behind trails of stars we now call stellar streams. These trails are littered with clues, ripples, disruptions, slight anomalies that may point to dark matter's hand at work. But these patterns also open up a deeper possibility. That dark matter isn't just a passive background force. It might be dynamic, structured, perhaps even behaving more like a fluid or a field than a sea of particles. In some models, dark matter may even self-interact, colliding or binding to itself in ways that form hidden shapes. This leads us to more exotic ideas. One theory gaining traction proposes that dark matter may consist of ultralight particles, like axions, whose wavelengths are so large they behave more like a wave than a particle. Imagine dark matter not as countless tiny marbles floating through space, but as a vast, invisible ocean of undulating energy, subtly warping everything it touches. In these models, dark matter doesn't just surround galaxies, it shapes their formation from the very beginning. In fact, many cosmologists now believe that without dark matter, galaxies wouldn't exist at all. In the early universe, just after the Big Bang, normal matter was too hot and energetic to clump together on its own. But dark matter, cold, quiet, stable, may have formed the first gravitational wells, the cosmic scaffolding that allowed atoms to begin clustering, cooling, forming stars, and birthing galaxies. Without dark matter, the universe might have been nothing but a smooth soup of hydrogen. No stars, no galaxies, no us. So we know it's there. We see its effects everywhere. But still, we ask, what is it? That's where simulations come in. At institutions like Princeton, Caltech, and CERN, scientists are running massive computational models of the universe. These simulations, like the Illustrious and Eagle projects, are virtual universes. They begin with conditions just after the Big Bang and evolve forward, governed by the laws of physics as we understand them. When they include dark matter, galaxies form beautifully. Spiral arms swirl, clusters and voids emerge. The cosmic web stretches across space in intricate patterns, but when they remove dark matter from the equations, the universe falls apart. These digital experiments confirm something deeply unsettling. Our understanding of cosmic structure only makes sense if something invisible is holding it all together. But that raises another possibility, one that scientists don't like to admit. What if we're not missing a particle? What if we're misunderstanding gravity itself? Some physicists have proposed alternative theories, like modified Newtonian dynamics, or MAO-ND, which tweak the equations of gravity at extremely low accelerations. In MOND, the strange motion of galaxies can be explained without invoking dark matter at all. Gravity simply behaves differently at vast cosmic scales. More recent variants, like TVS and emergent gravity, go even further. They suggest that what we call gravity might not be a fundamental force at all, but a side effect of deeper, more abstract principles, like entropy or information theory. These are radical ideas, beautiful ideas, but they come with problems of their own. MOND, for example, can explain galaxy rotation curves, but fails when applied to galaxy clusters, gravitational lensing, or the early universe. It doesn't fully replace dark matter, it just shifts the mystery to a different page. So we're left with a strange impasse. Our best theories require dark matter, our best experiments cannot find it, and our wildest ideas remain speculative. But let's not forget the scale we're dealing with. The universe is not just vast, it's ancient, it's subtle, it's complex in ways we may not yet be equipped to grasp. We may be ants trying to explain the architecture of a cathedral. It's possible that dark matter is not a single type of particle, but a whole dark sector, an entire suite of invisible particles and forces, as rich and varied as the visible matter we're made of. In this view, dark matter isn't just hiding, it's living in a hidden world, with its own rules, its own physics, maybe even its own complexity. That sounds like science fiction, but it's not. In fact, some models suggest that dark matter could form dark atoms, dark molecules, maybe even dark stars and dark galaxies. Entire structures that pass through ours like ghosts. There could be collisions, gravitational interactions, even dark matter black holes, all invisible, all undetectable, except through the faint tug of gravity. What if there's a mirror world overlaid on ours, touching it everywhere and yet forever separate? These digital experiments confirm something deeply unsettling. Our understanding of cosmic structure only makes sense if something invisible is holding it all together. But that raises another possibility, one that scientists don't like to admit. What if we're not missing a particle? What if we're misunderstanding gravity itself? Some physicists have proposed alternative theories, like modified Newtonian dynamics, or MAO-ND, which tweak the equations of gravity at extremely low accelerations. In MOND, the strange motion of galaxies can be explained without invoking dark matter at all. Gravity simply behaves differently at vast cosmic scales. More recent variants, like TVS and emergent gravity, go even further. They suggest that what we call gravity might not be a fundamental force at all, but a side effect of deeper, more abstract principles, like entropy or information theory. These are radical ideas, beautiful ideas, but they come with problems of their own. MOND, for example, can explain galaxy rotation curves, but fails when applied to galaxy clusters, gravitational lensing, or the early universe. It doesn't fully replace dark matter, it just shifts the mystery to a different page. So we're left with a strange impasse. Our best theories require dark matter, our best experiments cannot find it, and our wildest ideas remain speculative. But let's not forget the scale we're dealing with. The universe is not just vast, it's ancient, it's subtle, it's complex in ways we may not yet be equipped to grasp. We may be ants trying to explain the architecture of a cathedral. It's possible that dark matter is not a single type of particle, but a whole dark sector, an entire suite of invisible particles and forces, as rich and varied as the visible matter we're made of. In this view, dark matter isn't just hiding, it's living in a hidden world, with its own rules, its own physics, maybe even its own complexity. That sounds like science fiction, but it's not. In fact, some models suggest that dark matter could form dark atoms, dark molecules, maybe even dark stars and dark galaxies. Entire structures that pass through ours like ghosts. There could be collisions, gravitational interactions, even dark matter black holes, all invisible, all undetectable, except through the faint tug of gravity. What if there's a mirror world overlaid on ours, touching it everywhere and yet forever separate? If dark matter particles collide and annihilate, they might release energy, gamma rays, positrons, or other standard particles. Telescopes like Fermi and AMSO2 have picked up excesses, strange bulges of gamma radiation near the center of our galaxy, unexplained positron surpluses in cosmic rays. But the data is muddy, complex. Other sources, like pulsars or black holes, could account for it. Or maybe we're looking for the wrong kind of signal altogether, like tuning a radio to the wrong frequency, waiting for a song that never plays. And then there's a deeper philosophical challenge. What if we're not just failing to detect dark matter, but failing to define it? Because dark matter at its core is a placeholder. It's the name we've given to a behavior, a gap in our equations. Much like phlogiston or ether in the past, it's a concept that may one day be discarded, not because it was false, but because it was incomplete. What if dark matter isn't a thing at all? Enter emergent gravity, not a tweak of Newton, but a revolution. The idea that gravity itself is not fundamental, but emergent, like temperature or pressure, rising from the behavior of countless hidden variables. In this view, the effects we attribute to dark matter are really the echoes of unseen information woven into the fabric of space-time itself. This isn't fringe. Some of the brightest theoretical physicists in the world are exploring these ideas, and they're doing so because of an uncomfortable truth. We don't understand 95% of the universe. Dark matter is just the half of that puzzle. The other half is darker still. Dark energy. While dark matter pulls, dark energy pushes. While one binds galaxies together, the other tears them apart. They are opposites, and yet perhaps connected. Some speculative models suggest they might be two faces of the same phenomenon, or that both are artifacts of our limited perception, errors in our projection of a higher dimensional truth. String theory and extra dimensions have flirted with this idea for decades. If our universe is a three-dimensional membrane floating in a higher dimensional space, then gravity and its anomalies might be shaped by the geometry of that higher realm. In this scenario, dark matter might not be matter at all. It could be the gravitational shadow of another dimension pressing against ours. This is the domain of brain cosmology, a universe composed of layers, like sheets of paper in a book. Our sheet is not alone. Perhaps others press against it. Perhaps dark matter is the echo of mass in a neighboring universe whose gravity seeps through the cracks. It's a breathtaking idea and utterly unprovable for now. So where does that leave us? Back at the beginning, with a sky full of stars and space full of silence, with galaxies that spin too fast and theories that reach too far, with a question that haunts the heart of physics: what is the universe made of? Not just atoms and light, but the invisible, the unmeasured, the unexplained. The truth is, we don't know. But here's what we do know. Dark matter is not just a mystery. It's an invitation. It invites us to rethink physics, to build better detectors, launch better satellites, and craft better models. It forces collaboration across continents, across generations. It brings together mathematicians, astronomers, engineers, and philosophers, all chasing a shadow, all believing, despite decades of failure, that the answer is out there, that the universe, vast and strange as it is, still makes sense, that behind the darkness there is form, there is structure, there is something real, and that one day we'll see it. We stare into the night sky looking for stars, but the stars are only half the story. The real universe hides in the spaces between. The dark is not empty, it's alive. The stars are not quiet. They burn, pulse, and erupt with ancient fury. They echo across time, yet none speak. No signal, no message, no reply. If the universe is teeming with stars and planets, why is there such an oppressive silence? Why haven't we heard from anyone? This is the Fermi Paradox, the tension between the high probability of extraterrestrial civilizations and our complete lack of contact with them. The math seems to favor life. Frank Drake tried to formalize the idea in 1961 with the now famous Drake equation. a formula meant not to give an exact number, but to outline the variables involved in estimating how many advanced civilizations might exist in our galaxy. N equals R, Fp, Ne, Flti, Fc, Tesh L. Each term attempts to quantify one step in the development of communicative life. Rate of star formation, fraction of stars with planets, number of Earth-like worlds, the chance life appears, the chance intelligence arises, the development of detectable technology, and the duration such civilizations emit signals. Modern astronomy has pinned down the first few variables. There are over 200 billion stars in the Milky Way. Most have planets. Billions lie within habitable zones, the not too hot, not too cold region where water could exist in liquid form. And yet, despite these promising numbers, the skies remain eerily quiet. In 1950, physicist Enrico Fermi casually asked over lunch, "Where is everybody?" It's not just about life, it's about intelligent life, technological civilizations. If one had ever existed in our galaxy, it would only take a few million years, a blink on galactic timescales, to spread and leave unmistakable signs. Yet we see none. One possibility is sobering. Maybe we really are alone. Life might be extremely rare. Abiogenesis, the process where non-living matter becomes life, could be a freak event. Earth might have hit the cosmic jackpot against staggering odds. Even if simple life emerges often, intelligence might be rare. Earth hosted life for over 3.5 billion years, but only recently did a species capable of complex thought and tools arise. Dinosaurs ruled for 200 million years without building a single antenna. Maybe the emergence of advanced intelligence is not a natural outcome, just one strange path among millions, most of which end in silence. But if intelligence does arise, why haven't we seen evidence of expansion? Civilizations that can travel even at sublight speeds could, in theory, colonize the galaxy within a few million years. They could send probes, terraform planets, construct megastructures, yet we detect nothing. No Dyson spheres, no space traffic, no artificial energy patterns. There are theories. One of the most intriguing is the zoo hypothesis, the idea that alien civilizations intentionally avoid contact. Earth could be part of a vast, uncontacted preserve watched from afar. Our radio signals may be like tribal drums echoing through the forest, noticed but unanswered. It's a strangely comforting notion. We're not alone. We're simply being observed, perhaps even protected. Maybe there are cosmic rules. No contact until a civilization matures. But it raises practical concerns. How could multiple alien civilizations coordinate such strict secrecy? Why no leaks, no mistakes? Another answer is far more chilling: the great filter. This is the idea that somewhere along the path from prebiotic chemistry to interstellar empire lies a nearly insurmountable obstacle, a filter that very few, if any, make it through. If the filter is behind us, say at the level of abiogenesis or multicellular evolution, we may already be exceptional, survivors, a miracle. But if the filter lies ahead of us, the implications are grim. That would mean intelligence arises, develops technology, and inevitably destroys itself. Nuclear war, climate collapse, unchecked AI, engineered pandemics, technologies with power beyond our wisdom. Every silent world out there could be a warning. Civilizations might flicker into existence only to annihilate themselves in bursts of hubris and confusion. We may be on the verge of discovering not aliens, but our own fragility. There are other possibilities. Maybe alien life is common, but completely unlike us. Not carbon-based, not biological, not physical in a form we understand. What if advanced life sheds its biology, becomes digital, merges with machines, becomes energy or quantum phenomena? They could live in places we don't even think to look. Inside stars, in the vacuum between galaxies, inside engineered black holes, or as consciousnesses in simulated realities. We're searching for a very specific kind of signal, a narrow radio beam aimed directly at Earth. What if that's not how advanced life communicates? What if they've evolved past communication entirely? To us, intelligence means curiosity, exploration, contact. But that could be projection. Maybe the drive to expand is a phase, one that fades. Civilizations might reach technological heights, then turn inward, create perfect virtual realities, lose interest in the stars, or maybe they hide. There's the dark forest theory, a terrifying thought experiment. Imagine the universe as a dark forest. Every civilization is a hunter, silent, careful, aware that the forest is full of other hunters. To announce your presence is to risk destruction. So everyone hides, everyone listens, no one speaks. Because in the dark forest, safety lies in silence. It makes a terrible kind of sense. A single broadcast could expose you to unknown dangers. The first civilization to speak might be the first to die. Earth has been sending signals for over a century, leaking out into the cosmos. We've already announced our presence. If others follow the dark forest logic, they may now see us, but we can't see them. It's also possible that we're simply too early. The universe is 13.8 billion years old, but intelligent life may be rare and young. We could be among the first. We might be the dawn chorus, the first voices stirring in the vast cosmic morning. There's one more unsettling idea. Maybe intelligence is not an evolutionary advantage, but a cosmic mistake. Life by nature tends to balance itself within ecosystems. It adapts, consumes within limits. Intelligence disrupts that balance. It changes environments, invents tools of destruction, pursues progress without knowing what lies ahead. Civilizations might rise, reach the edge of space, and collapse under the weight of their own brilliance. Maybe the Great Silence is not a riddle to solve, but a law of nature. Intelligence may be unstable, like a fire that burns too brightly, then consumes itself. And yet, despite all this, we search. SETI continues its work, scanning the heavens for signals. New technologies allow us to look deeper, more precisely, more broadly. AI systems comb through petabytes of data looking for anomalies. Optical, infrared, radio, we leave no stone unturned. Once, we found something. August 15, 1977, a burst of signal from the Sagittarius constellation. Narrowband, strong, lasted 72 seconds, no known natural origin. The astronomer who found it circled the printout and wrote one word, "Wow!" The signal never repeated. It was never explained. Some think it was interference. Others believe it was the best candidate we've ever had. In all the years since, nothing like it has returned. For all our scanning, all our equations, all our theories, the sky remains mute. Maybe the universe is full of life. Maybe it's empty. Maybe we're early. Maybe we're doomed. But we keep listening, because one day, through static and starlight, we might hear a voice, and everything will change. The mystery of the silence continues, but it is not simply a case of waiting for a signal. Over the decades, astronomers and scientists have offered an array of explanations, not just for the absence of signals, but for why we may never receive one. The SETI, Search for Extraterrestrial Intelligence program, has become the focal point of the hunt for alien life. It uses radio telescopes to scan the sky for any signs of electromagnetic signals that might be coming from extraterrestrial civilizations. The search initially began with simple radio frequencies, hoping to find a burst of energy from a distant alien civilization using technology similar to ours. Yet, even with all the advancements in technology, there has been no definitive proof of an alien signal. The difficulty is that the universe is vast. The Milky Way alone contains over 200 billion stars, each possibly surrounded by planets. As of today, scientists have detected thousands of exoplanets, some of which lie within the habitable zone of their stars, where life-supporting conditions could exist. Despite the size of the search, the vastness of space means that even with the best technology, our ability to detect signals is limited. Radio signals, for instance, degrade over vast distances. A transmission from a civilization 1,000 light years away would be faint by the time it reached Earth, buried in the background noise of the cosmos. Even a signal from just 100 light years away would be very weak by the time it reached us. This makes the odds of catching a signal from an alien civilization extremely slim, especially given the fact that we're not even sure what to listen for. Even with this vast search area, the mystery deepens. Some scientists believe the problem lies not in the search area, but in the method of the search itself. We're looking for the wrong kind of signals, they argue. The standard assumption is that any intelligent alien civilization would be sending out strong, detectable radio signals, perhaps even on the same frequencies as early human radio signals. But what if alien civilizations communicate in ways we haven't yet thought to search for? If they've mastered new technologies or evolved beyond biological constraints, their methods of communication might be unrecognizable to us. It's important to ask, why would a technologically advanced civilization continue to use radio signals, which are easily detectable and prone to decay over long distances? It's conceivable that they would have moved beyond electromagnetic communication entirely. The progression of technology on Earth alone has moved from telegraphs to satellites to fiber optic cables to quantum communication. Perhaps alien civilizations are using advanced technologies that we simply don't understand. Quantum entanglement, neutrino beams, or even methods of communication that are beyond our current comprehension. Additionally, we might be overlooking a more subtle form of communication. Gravitational waves, for example, have been detected by scientists here on Earth as ripples in the fabric of space-time caused by massive objects like black holes merging. The detection of these waves is groundbreaking as they offer us a completely new window into the universe. But could they also serve as a means of communication for advanced civilizations? We haven't yet developed the technology to detect gravitational waves at the precise scale needed to interpret them as messages, but in the future, it's possible that such signals could be the key to discovering extraterrestrial intelligence. Yet even more troubling is the possibility that we may not even be listening at the right time. The window for detecting extraterrestrial signals could be incredibly brief. Civilizations might arise, develop the capability to send signals, and then self-destruct or evolve past the need for communication. The technological lifespan of a civilization might be shorter than we imagine. In fact, according to some experts, there may be a cosmic golden age when civilizations capable of communication are rare, and in that brief moment we could make contact. But if we miss that window, it may be too late to hear from them. A particularly chilling theory regarding why we haven't detected alien life is the dark forest hypothesis, which was proposed by Chinese science fiction author Liu Cixin in his novel The Three-Body Problem. According to this theory, the universe is akin to a dark forest, and civilizations are the hunters. In this forest, there's no way to know who is nearby, and the safest strategy is to remain silent and unseen. Every civilization must assume that any other civilization is a potential threat. After all, they may have weapons or technology far more advanced than ours. As a result, all civilizations hide in the dark, making no noise, broadcasting no signals, and revealing nothing about themselves. The logic behind this hypothesis is straightforward. If you send out a signal, you reveal your position, and any civilization that detects it could decide to destroy you before you can grow powerful enough to pose a threat. This creates a situation where all intelligent life is forced into silence to ensure survival. The dark forest hypothesis is a stark contrast to the idealistic view of the universe being full of friendly civilizations waiting to make contact. Instead, it suggests that the silence we experience is due to a cosmic game of survival of the fittest, where communication could be the trigger for conflict, not cooperation. If this hypothesis holds any merit, it suggests that intelligent life exists, but it remains hidden for survival. This is a terrifying notion, as it paints a picture of a universe full of advanced beings, each carefully concealing their existence to avoid drawing attention. The fact that we haven't heard from anyone could be the result of universal caution, an attempt by all civilizations to avoid being the next target. Another possibility for the silence comes from the theory of self-destruction. This concept proposes that intelligent civilizations inevitably destroy themselves before they ever get the chance to explore space or communicate with others. This idea draws from the reality that, on Earth, we have advanced to the point where we possess the means to destroy ourselves. Nuclear weapons, environmental degradation, and the threat of runaway technology like artificial intelligence. Given the rapid rate at which we've developed these technologies, it's plausible that other civilizations might also have discovered powerful tools that could lead to their own destruction. They may develop technologies that are too powerful to control or engage in destructive behavior that eliminates their civilization before they can establish interstellar contact. The Great Filter Theory connects to this idea, positing that there may be one or more major hurdles that civilizations must overcome to avoid self-destruction. If these filters are common, it could explain the silence we hear. It's possible that the emergence of intelligent life is not as rare as we think, but that civilizations are often short-lived, unable to surpass the technological or environmental challenges that inevitably lead to their downfall. This raises another question. If we are lucky enough to survive, what will it take for humanity to avoid the same fate? Are we progressing toward a future where we can control our technologies, or are we destined to follow the same path as those who came before us, reaching the stars only to implode upon ourselves? Could the silence be a result of cosmic indifference? Perhaps the universe is simply too vast, too indifferent, to harbor intelligent life capable of communication. Many of the explanations proposed so far assume that other civilizations are actively trying to reach out, but what if they aren't? What if, in the grand scale of the cosmos, civilizations don't bother to communicate or expand beyond their homeworlds? The idea that a civilization could evolve, thrive, and decide that exploration is not worth the effort is difficult to grasp, but it may be true. Humanity's own trajectory, in some ways, reflects this. While we've launched satellites and probes into space, we are far from colonizing other planets or searching in earnest for alien life. Some might argue that civilizations reach a point where their needs are met on their homeworld, and the expansion into space becomes irrelevant, even unnecessary. This indifference could be the ultimate reason why we hear nothing. Civilizations may grow comfortable in their own spheres, and space exploration or intergalactic communication may not be part of their priorities. Time is one of the most fundamental aspects of our reality, yet its true nature remains one of the greatest mysteries in science and philosophy. We all experience time as a continuous flow from past to present to future, yet time itself is a concept that we struggle to understand fully. What is time, and why does it behave the way it does? Could time be something more than just a dimension, something that may have a deeper meaning yet to be discovered? One of the most perplexing features of time is its directionality, often referred to as the arrow of time. We experience time as a one-way progression, always moving forward from the past into the future. But why is this the case? Why doesn't time work in reverse, as we see in many physical laws? In the laws of physics, such as Newton's laws of motion or even Einstein's theory of relativity, there is no inherent direction of time. These laws are symmetrical. They work just as well whether time is moving forward or backward. Yet in our daily experience, we never see time moving backward. We never see broken glasses spontaneously reassemble or the past suddenly catch up with us. So what causes the arrow of time to point in only one direction? The answer may lie in entropy, a concept in thermodynamics. Entropy refers to the degree of disorder or randomness in a system. According to the second law of thermodynamics, the total entropy of an isolated system tends to increase over time, meaning that systems naturally evolve toward more disordered states. This increase in entropy is often associated with the forward flow of time. In simple terms, time seems to move forward because the universe is always becoming more disordered and less predictable. While this explanation seems reasonable on the surface, it doesn't fully account for why we experience time as flowing in one direction. After all, entropy applies to all systems, and yet we still have the experience of time moving forward, or at least we assume it does. Could there be another factor at play, one that governs the flow of time on a more fundamental level? The nature of time becomes even more puzzling when we consider its origins. According to the widely accepted model of cosmology, time itself began at the moment of the Big Bang. The Big Bang represents the birth of both space and time, which means that before this event there was no before. Time itself did not exist. This raises profound questions. How can time have a beginning? And if time had a starting point, could it also have an ending point? These questions are at the heart of one of the most significant unsolved mysteries in modern science. While we have a general understanding of the events that occurred after the Big Bang, we have no clear explanation for what happened at the exact moment when time itself began. Einstein's theory of general relativity revolutionized our understanding of time by showing that time is not an absolute, universal constant. Instead, time is relative and can be affected by gravity. This phenomenon, known as time dilation, means that time passes at different rates depending on how fast you are moving and how close you are to a massive object like a planet or star. Time dilation has been experimentally confirmed in a variety of ways. For instance, atomic clocks placed on airplanes traveling at high speeds show that time passes slightly slower for the clocks in motion compared to those on the ground. This is a direct result of the fact that the speed of light is constant, and as objects approach the speed of light, their experience of time slows down relative to an observer at rest. Another example of time dilation occurs near massive objects, such as black holes. The closer an object is to a black hole, the more time appears to slow down relative to an observer far away from the black hole's gravity. This effect becomes extreme near the event horizon, the point of no return around a black hole. Time, as experienced by an object falling into a black hole, slows down drastically as it approaches the event horizon, and from the perspective of an outside observer, time seems to stop completely at the event horizon. This bending of time is not just an abstract concept. It has real, measurable effects on our daily lives, particularly in the context of global positioning systems, GPS. GPS satellites orbit Earth at high altitudes and travel at high speeds, meaning that their clocks tick slightly differently than those on Earth. Engineers have to account for both special relativity due to the satellite's motion and general relativity due to the gravitational effects of Earth to ensure that the GPS system provides accurate location information. While time dilation is well understood in these contexts, it still raises intriguing questions. If time can be affected by speed and gravity, does this imply that time is somehow a physical property of the universe, something that can be manipulated or altered? Could we, one day, harness the ability to control time or travel through it in ways we currently can't imagine? The concept of time travel is one of the most popular topics in science fiction. The idea that we might one day be able to travel backward or forward in time has captured the imagination of countless writers, filmmakers, and theorists. But is time travel possible according to the laws of physics? Einstein's theory of general relativity does provide some theoretical grounds for time travel. For example, the closed time-like curves, CTCs, predicted by the equations of relativity, suggest that it might be possible to travel backward in time by following a loop through space-time. However, these loops require conditions that are far beyond our current technological capabilities. For instance, traveling faster than light, which is necessary for these closed loops, would violate our current understanding of the laws of physics. Even if time travel were possible, it would come with a host of paradoxes and logical dilemmas. The most famous of these is the grandfather paradox. What would happen if you traveled back in time and killed your grandfather before your parent was born? If your parent was never born, you could never have existed to travel back in time in the first place, creating a logical contradiction. This paradox has led many physicists to suggest that time travel may not be possible after all, or that if it is, there must be mechanisms in place to prevent these paradoxes from occurring. Some theories propose that time travel might be allowed, but only in ways that don't violate causality, the principle that cause precedes effect. One suggestion is the many worlds interpretation of quantum mechanics, which proposes that every possible outcome of an event creates a new, parallel universe. According to this theory, if you were to travel back in time and alter something in the past, you wouldn't change the present timeline. Instead, you would create a new, parallel timeline where events unfolded differently. Yet, while time travel remains a tantalizing possibility, it also seems to be one of the most difficult aspects of our understanding of the universe. Whether it is possible or not, the questions it raises about the nature of time, reality, and causality continue to challenge the limits of science and philosophy. One of the most fascinating and mind-bending mysteries of the universe revolves around the concept of black holes. These regions of space-time are so dense that nothing, not even light, can escape their gravitational pull. Black holes challenge our understanding of physics, and despite decades of research, much about them remains a mystery. What exactly happens inside a black hole? How do they form? And what role do they play in the grand scheme of the universe? At the heart of a black hole lies the singularity, a point of infinite density where the gravitational forces are so intense that they overwhelm all other forces of nature. The singularity represents a breakdown of the laws of physics as we understand them. According to general relativity, the fabric of space-time becomes infinitely curved at the singularity, and the usual concepts of space and time no longer apply. Yet, this presents a significant problem. General relativity, which describes the behavior of large-scale objects like planets and stars, breaks down at the singularity, and we must turn to quantum mechanics, which governs the behavior of the smallest particles in the universe. But when we try to combine these two frameworks, general relativity and quantum mechanics, we run into a conflict. The rules of quantum mechanics don't seem to work in the extreme environment of a black hole. This is one of the biggest unsolved problems in modern physics, and it highlights the need for a theory of quantum gravity, a framework that could unify both general relativity and quantum mechanics. One of the most intriguing aspects of black holes is the concept of the event horizon, the boundary beyond which nothing can escape. Once an object crosses the event horizon, it is effectively lost to the black hole, unable to return. The event horizon marks the point at which the escape velocity, the speed needed to escape the gravitational pull, exceeds the speed of light. This means that no matter or radiation can escape from inside the event horizon, making black holes invisible to direct observation. The only way we can detect black holes is through their influence on nearby matter. However, recent advancements in technology have given us unprecedented insights into the behavior of black holes. In 2019, the Event Horizon Telescope, EHT, collaboration produced the first ever image of a black hole. The image showed the shadow of the supermassive black hole at the center of the galaxy M87, providing direct evidence of black holes' existence and their ability to warp light around them. This historic image has opened up a new era of black hole research and has raised even more questions about these mysterious objects. One of the most puzzling phenomena associated with black holes is the information paradox. According to quantum mechanics, information about the state of a system cannot be destroyed. This principle, known as unitarity, implies that the information contained within an object should be preserved even if the object falls into a black hole. However, general relativity suggests that when an object crosses the event horizon, it is effectively lost forever. This creates a paradox. If information is lost inside the black hole, it would violate the fundamental principles of quantum mechanics. The information paradox was famously posed by physicist Stephen Hawking in the 1970s. He suggested that black holes might slowly evaporate over time through a process known as Hawking radiation. This radiation arises due to quantum effects near the event horizon, where virtual particle pairs are constantly popping in and out of existence. Occasionally, one of these particles will fall into the black hole while the other escapes, carrying away energy in the form of radiation. Over time, this radiation would cause the black hole to lose mass and eventually evaporate, potentially resolving the information paradox by releasing the information trapped inside. However, the true nature of Hawking radiation and its implications for the information paradox remain unclear. Some researchers propose that the information could be encoded in the radiation emitted by the black hole, while others suggest that it might be stored in a holographic form on the event horizon, preserving the information without violating quantum mechanics. These ideas are still speculative, and the resolution of the information paradox is one of the most active areas of research in theoretical physics. Another perplexing aspect of black holes is their role in the formation of galaxies and the evolution of the universe. Supermassive black holes, which can be millions or even billions of times more massive than the Sun, are found at the centers of most large galaxies, including our own Milky Way. It is believed that these supermassive black holes formed early in the history of the universe, perhaps from the collapse of massive gas clouds or the merger of smaller black holes. The presence of supermassive black holes at the center of galaxies suggests that they may play a key role in regulating galaxy formation and growth. One of the most surprising discoveries in recent years is the observation that the size of a galaxy appears to be closely linked to the mass of its central black hole. This relationship, known as the M-sigma relation, suggests that the growth of supermassive black holes and their host galaxies is interconnected. Some theories propose that the energy released by black holes through processes such as accretion, where matter is drawn into the black hole and heated to extreme temperatures, could influence the rate of star formation in the surrounding galaxy. Despite their destructive nature, black holes may also serve as cosmic engines that help shape the universe. The energy released by black holes through jets of matter and radiation can affect the surrounding environment, creating powerful winds and radiation that can influence the formation of stars and galaxies. In this sense, black holes might not only be destroyers, but also creators, playing a central role in the evolution of the cosmos. As our understanding of black holes continues to evolve, we are faced with even more questions. How do black holes form in the first place? What happens inside the event horizon? Can we ever truly understand what occurs at the singularity, or will it remain a mystery beyond our reach? The more we learn about black holes, the more we realize how much we have yet to discover. The mystery of the Fermi Paradox revolves around one of the most profound questions in the search for extraterrestrial life. If the universe is so vast and filled with potentially habitable planets, why have we not yet encountered any signs of intelligent alien life? This paradox, named after physicist Enrico Fermi, highlights the contradiction between the high probability of extraterrestrial civilizations existing and the complete lack of evidence for them. Despite decades of searching, we have yet to find any definitive proof of alien life. So where is everyone? To understand the Fermi Paradox, we first need to consider the vastness of the universe. The observable universe is estimated to contain over 100 billion galaxies, each with hundreds of billions of stars. Many of these stars likely have planets orbiting them, and a significant number of these planets may be in the habitable zone where conditions could be right for life to form. In fact, recent discoveries of exoplanets, planets outside our solar system, have revealed that there are potentially billions of habitable worlds in our galaxy alone. Given these odds, scientists have developed the Drake equation, which attempts to estimate the number of extraterrestrial civilizations in our galaxy. The equation takes into account factors such as the number of stars that form each year, the fraction of those stars with planets, the number of planets that could support life, and the likelihood that intelligent life will emerge. While the equation's specific values are still debated, many scientists believe that there should be a large number of alien civilizations spread across the Milky Way. However, despite the high probability of life existing elsewhere in the universe, we have found no definitive signs of intelligent alien civilizations. This is where the paradox lies. If the universe is so vast and teeming with potentially habitable planets, why is there no evidence of extraterrestrial life? Why haven't we received any signals, detected alien spacecraft, or found any traces of advanced technologies? There are several possible explanations for this paradox. One of the most straightforward possibilities is that intelligent alien civilizations may exist, but they are simply too far away for us to detect. Even if alien civilizations are out there, the vast distances between stars could make communication or travel between them impossible with current technology. The speed of light, which is the fastest speed at which information can travel, is simply too slow to bridge the enormous gaps between stars in a human lifetime. This means that even if aliens were trying to contact us, their signals could take thousands or even millions of years to reach us. Another possibility is that extraterrestrial civilizations are rare and may only emerge under very specific conditions. It's possible that intelligent life requires a combination of factors that are exceedingly rare, such as the right chemical composition, a stable climate, and a planet capable of supporting life over billions of years. The evolution of intelligent beings, like humans, may be an exceedingly rare event, with most planets only harboring microbial life or no life at all. In this scenario, the likelihood of an advanced civilization existing at the same time as humanity is extremely low. Alternatively, some researchers believe that advanced alien civilizations may be out there, but that they might be deliberately avoiding us. One theory suggests that alien civilizations may follow a prime directive of non-interference, similar to the fictional concept depicted in Star Trek. This theory proposes that advanced civilizations are aware of us, but they deliberately avoid making contact in order to prevent disrupting our natural development. The idea is that extraterrestrials may see us as a primitive species, and refrain from engaging with us until we reach a certain level of technological or social maturity. Others have proposed the idea that alien civilizations could be using technologies that are beyond our comprehension, making it impossible for us to detect them. Perhaps aliens are communicating in ways we cannot yet understand, such as through advanced forms of quantum communication, or they may be using methods of travel that are so advanced they appear to us as if they are not even there. We might be missing the signals because we don't yet know what to look for. One particularly intriguing idea is that intelligent civilizations might have a short lifespan. When it's possible that advanced civilizations have a tendency to self-destruct before they can develop the ability to communicate across interstellar distances. This could be due to war, environmental collapse, or other factors that lead to the extinction of intelligent life before it can spread beyond its home planet. In this scenario, the universe could be filled with the ruins of civilizations that once existed, but were wiped out before they could make contact with other intelligent species. Another explanation for the Fermi Paradox is the possibility that intelligent life has already contacted us, but we have failed to recognize it. Some argue that alien civilizations could be visiting Earth or sending signals, but these encounters are either not being detected or are being dismissed as hoaxes or misunderstandings. The phenomenon of UFOs and alien abductions could, in some interpretations, be evidence of alien contact that we simply do not yet understand. However, these claims remain highly controversial, and there is no scientific consensus on their validity. Another explanation for the Fermi Paradox is the possibility that intelligent life has already contacted us, but we have failed to recognize it. Some argue that alien civilizations could be visiting Earth or sending signals, but these encounters are either not being detected or are being dismissed as hoaxes or misunderstandings. The phenomenon of UFOs and alien abductions could, in some interpretations, be evidence of alien contact that we simply do not yet understand. However, these claims remain highly controversial, and there is no scientific consensus on their validity. Until we develop the tools and perhaps the perspective to truly recognize what alien contact might look like, we may continue to overlook the very answers we seek.